Welcome all. In previous lecture we have seen half adder, half subtractor, full adder, full subtractor and their design. Today we will see how to construct a n-bit parallel adder or subtractor using full adder and full subtractor. A full adder is capable of adding two single digit binary numbers along with the carry input, but in practice we need to add binary numbers which are much larger in size than just 1 bit. So the two binary numbers to be added could be of 4 bit, 8 bit or 16 bit long in size. In general, we assume that both the numbers are n bit long. To add n bit binary numbers, we need to use a n bit parallel adder as shown in this figure. It uses full adders which are connected in cascade, and carry output of previous full adder is connected to the carry input of next full adder. These are the full adders. This is full adder 0, this is full adder 1, this is full adder 2 and this is full adder n-1, as we have considered n bits for addition. Now here these are the two inputs of the full adder, basic inputs, and third input is this carry input. The previous carry output of a full adder is connected as a carry input to the next full adders, and these are the sum outputs of the full adders. Now we will see how a 4-bit parallel adder can be constructed using full adders. The black diagram of 4-bit parallel adder is shown in figure, which can add 4 bits. Let the two 4 bits word that are to be added are A and B as follows. The A word consists of 4 bits, that is A3, A2, A1, A0, and a B word consists of 4 bits, that is B3, B2, B1, B0. A0 and B0 represents LSB bits, whereas A3 and B3 are the MSB bits of word A and B. Here this is a full adder 0, it is named as 0, it is named as 1, it is named as 2 and it is named as 3. These are the 4 bits of two numbers A and B. This is A0, B0, A1, B1, A2, B2, A3, B3. As we starts addition from LSB, the LSBs are given as an input to this first full adder, that is A0, B0, and we ends the addition with the MSB. So the MSB A3 and B3 are given as an input to the last full adder, that is full adder 3. Now here carry input of previous full adders are connected as a carry output of previous full adder are connected as a carry input to the next full adder, and the first carry input is connected to ground, as there will not be any carry during the initial addition of LSPs. So the carry input of first full adder is connected to ground by default. This C out of last full adder represents the final carry output of our 4-bit addition of two numbers. These are the 4-bit addition results, that is S3, S2, S1, S0. This is how we can construct a 4-bit parallel adder using full adders. If we want to construct 8-bit full parallel adder, we can use 8 full adder. For 16-bit parallel addition, we can use 16 full adders, so on. Now this is the generalized diagram of this 4-bit parallel adder. The bits A0, A1, A2, A3 are represented together like this. The bits B0, B1, B2, B3 are represented together to form a word B, and this is a word A. This is the carry input of our 4-bit parallel adder. After addition, we get this sum output. S3, S2, S1, S0 are written together, and after addition we get the final carry also. So these two are equivalent with each other. Now we will see a 4-bit parallel adder IC 7483 and 74283. These are the two ICs of 4-bit parallel adder which can add two 4-bit numbers. This is the operand 1, that is first number. This is the operand 2, that is second number, each of 4 bits. Again, this is the carry input and this is the final carry output, and these are the sum outputs. This is the pin configuration of IC 7483, which is going to act as a 4-bit parallel adder. Now out of this operand 1, the 4 bits are at this is B3, this is B4, this is B1, and this is B2. These are the 4 inputs of operand 1. Again, A4, A3, A2 and A1 are the another 4 inputs of second number, that is operand 2. Now S3, S2, S1 and S4 are the sum output. The VCC is connected to pin number 5 and ground is connected to pin number 12. A C input is connected at pin number 14 and C output will going to appear at pin number 13. This IC is of 16 pin. This is the notch, and to the left side of the notch there will be a pin number 1, starting from pin number 1 to 8 and 9 to 16. This is how a IC 7483 can be used as a 4-bit parallel adder. This configuration is needed for us during the practical, so that we can connect the inputs to particular pins using this pin configuration of ICs. This is the 4-bit parallel adder using IC 7483. That is, the diagram is same like this. So a 7483 IC is having 4 inputs of one number, that is A0, A1, A2, A3. Another input is number B having 4 bits B0, B1, B2, B3. After addition of these two 4 bits, we get the sum of 4 bits, that is S0, S1, S2, S3. A Cin is connected first carry input of first full adder is connected to ground by default, and this is the final carry output of a 4-bit parallel adder. Now if you want to add two 8-bit numbers using 4-bit parallel adder, IC 74283 or 7483, then we have to cascade two 4-bit adders. That is, by cascading two 4-bit adders we can add two 8-bit numbers. Suppose the two 8-bit numbers are A and B. A is of 8 bits from A7 to A0, B is also of 8 bits from B7 to B0. These numbers we have to add using 74283 IC or 7483 ICs, which are of 4-bit adders. Now out of A7 to A0, first 4 bits are connected to the first 4-bit adder 1. Next 4 bits of number A, that is A4 to A7, are connected as a 4-bit inputs to this adder 2. Again from another number, that is B, first 4 bits, that is B0 to B3, are connected as input to this first adder, and next 4 bits, that is B4 to B7, are connected as a input to this second adder. Again the initial carry input is connected to ground. Last carry output of first 4-bit adder, that is adder 1, is connected as a carry input to the next 4-bit adder, that is adder 2. The carry output of second 4-bit adder, that is adder 2, will be the final carry output. The sum of 8 bits, from which first 4 bits are from adder 1, it is S0, S1, S2, S3, and next 4 bits of sum are from adder 2, that is S4, S5, S6, S7. This is how we can cascade two 4-bit adders to add two 8-bit numbers. Now next we will see a 4-bit parallel subtractor using 2's complement. The circuit is same, the only difference is here the number B is given through these NOT gates and a carry input is connected to VCC. Now we know binary subtraction rules using 2's complement method, in which first we find the 1's complement of B. After that we find 2's complement of B by adding a 1 into the 1's complement of B. After that we add A and 2's complement of B using binary addition rule. After that we check for carry. If carry generated is 1, then the result obtained is positive and is in true form. If carry generated is 0, then the result obtained is negative and is in 2's complement form. Then we have to take 2's complement of the result to convert it into the true form. This all we have studied in the first unit, that we are going to implement for the circuit design. Now here this is the circuit of 4-bit parallel subtractor. The number to be subtracted, that is B, is first passed through the inverters to obtain 1's complement of number B. one inverter per bit of word B is used. So here are 4 inverters to convert 4 bits of number B into the ones complement form. After that we are going to add 1 into the ones complement of B. Here we get ones complement of B. Here we are going to add a 1 through the carry input so that we can get 2's complement of B. Therefore this carry input is permanently connected to plus VCC, which will provide a carry input of 1, by which we get 2's complement of number B, which is to be subtracted. The 4-bit adder then adds this number A and 2's complement of B to produce a subtraction at its sum outputs, that is S0, S1, S2, S3. The word S0, S1, S2, S3 represents the result of binary subtraction A minus B, and the carry output represents the polarity of the result. If carry output is 0, then the result is in negative form, so we have to take a 2's complement of this sum. If carry output is 1, then the result obtained is in positive form, so we no need to do anything on the sum which we get using this adder. This is how we can subtract the 4-bit to 4-bit numbers using a 4-bit adder by connecting simply the number B as a input through NOT gates and this carry input connected to the plus VCC permanently. These are the only 2 modifications which we have to do in the adder circuit to act it as a subtractor circuit. Again, these are the steps explained in this PPT for the operation of this adder as a subtractor. You can go through this. Thank you.